In this lecture, we're going to introduce the Hertzsprung-Russell diagram. The Hertzsprung-Russell diagram is one of the most important diagrams in astronomy. It looks simple, a plot of luminosity versus color index, and yet as we're going to learn through the course of this lecture and those that follow, the Hertzsprung-Russell diagram carries within it all of the clues we need to unravel the problem of stellar structure and evolution. Remember from previous lecture that to a good approximation, the spectrum of a star is a black body with a characteristic temperature T. For example, the Sun has a temperature of its photosphere of about 5,770 degrees Kelvin. The black curve is the actual spectrum of the Sun. The green curve running through it is the spectrum of a 5,770 degree Kelvin black body of the same luminosity. We notice that the Sun is not a perfect black body, but is a black body heavily modified by atoms and molecules in the atmosphere of the Sun. The color of a star is determined by its temperature. Again, stars are approximately black bodies. Hotter stars will be bluer, and cooler stars will be redder. So that a 6,000 degree Kelvin star will have most of its energy emerging at blue and ultraviolet wavelengths, and so appear blue to the eye. A star of nearly 5,000 degrees Kelvin will have a nearly even mix of colors across the spectrum, but a little bit of a tilt towards the redder portion of the spectrum, and so it looks like a slightly reddish white. By 4,000 degrees Kelvin, a spectrum of a 4,000 degree Kelvin blackbody is very strongly skewed to the red part of the visible spectrum, and the star takes on a notably reddish hue. By the time we reach 3,000 degrees Kelvin, most of the energy is emerging in the infrared part of the spectrum, and the star becomes decidedly red. Again, the basic principle is very clear. The hotter a star, the bluer its color. The cooler a star, the redder its color. So the color of a star is a proxy for the temperature of the star. And in practice, temperature is often a lot harder to measure than the spectral color. The luminosity of a star, the total amount of power of the star, the energy per second pouring off of the star, is determined by its temperature of the photosphere and by the radius of the photosphere. And this is given through the formula that the luminosity is equal to 4 pi times the radius squared times a constant sigma times the photosphere temperature to the fourth power. For example, consider a star of temperature 6,000 degrees Kelvin with a radius Ra. If we have another star B with the same radius but different temperature, here a star that's half the temperature, the luminosity of star B will be related to the luminosity of star A simply through the ratio of their temperatures to the fourth power. In the case of 3,000 to 6,000, this will be in the ratio 3,000 to 6,000 to the fourth power. 3,000 over 6,000 is 1/2. 1/2 to the fourth power is 1/16. So star B in this case, even though it is the same radius, because it's half the temperature, it's 1/2 to the fourth, or 1/16 as luminous as star A. If a third star has the same temperature as star A, but is 2 times larger radius, so same T, different R, in this case, the luminosity of star C will be related to the luminosity of star A through the ratio of their radii squared. Because star C is 2 times bigger than star A, the luminosity of C will be 2 squared times LA, or 4 times the luminosity of star A. So same temperature, different radius, the bigger star is more luminous. Same radius, different temperature, the hotter star is more luminous. The hot, dense photosphere that we characterize by a blackbody spectrum is not all the end of the star. The star actually doesn't have a solid surface. The atmosphere of the star can extend quite a ways out into space. And it's this thin, slightly cooler atmosphere that gives rise to the absorption spectrum. The dense photosphere emits a blackbody spectrum, as shown by the green curve here, representing the blackbody curve for the Sun. However, this blackbody spectrum does not come to us directly, but has to pass through the cooler outer atmosphere of the star. And as a consequence, atoms and molecules in the star's atmosphere absorb some of this light coming off the photosphere, imprinting dark absorption lines on the spectrum. We see here the spectrum of the Sun, which is characterized by a photosphere with a 5,770 degree Kelvin blackbody, but because we cannot view that blackbody directly, only the blackbody pass through the cooler outer atmosphere of the sun, we see that blackbody modified. It's had the absorption from atoms and molecules imprinted onto it. This is a detailed spectrum of the sun. We've seen this picture before. This is taking a spectrum of the sun and wrapping it around on itself and color-coding it. We can see the general rainbow wash of color from blue through green, yellow, orange, and red as we go from high energy to low energy light. But superimposed upon this blackbody spectrum are a series of dark absorption lines. These lines are lines like over here is the lines of hydrogen, a pair of lines of sodium, a triplet of lines of magnesium, and many of the smaller lines here belong to neutral and ionized metals, principally iron. Here's the spectrum of a bright star from the summer sky, the bright star Vega in the constellation of Lyra. Vega is a hotter star than the sun, with a temperature of 9,600 degrees Kelvin. We see the characteristic blackbody shape of a 9,600 degree Kelvin blackbody heading off towards blue and ultraviolet wavelengths on the left, but crossing this spectrum are a series of dark absorption lines that we recognize as arising from the hydrogen atom in the atmosphere of this star. It was noticed early on that different stars have different spectra and different spectral lines. At first, people thought this was due to differences in composition. In the early days, all people could do was really attempt to classify them. In the late 19th century, it was found that the patterns of spectra of stars, while unique from star to star, showed certain repeating patterns, that different types of stars could be classified together by the general appearance of their spectrum. Bear in mind that in the late 19th century, spectroscopy was still in its early days. We did not yet have a good theory of the atom, did not understand how spectral lines emerged from atoms and molecules. Chemists had characterized the spectra of atoms, but had no understanding of the mechanism. Still, with this tool in mind, people thought that perhaps the spectra were going to give us a window onto the composition and conditions inside the stars. One of the astronomers who set about trying to understand the spectral classification of stars was Edward Pickering at the Harvard University. He led a program to obtain photographic spectra of nearly 220,000 stars using telescopes in the northern and southern hemispheres and the then brand new technology of large glass plate photography. To be able to analyze all of these spectra required that a human being look at them. This is the day before electronic computers, and indeed, the very first computers in history were not machines, but people. In this case, these were women who were hired by Edward Pickering and trained in the analysis of the spectra. Remember, in the late 19th and early 20th century, the women often did not work outside of the home, and therefore they represented a highly educated and very willing workforce that unfortunately at the time could not find an output for their considerable talents in the workplace. So as a consequence, Pickering was able to allow many of these women, many of whom had college educations but could not get jobs, to play a vital role in the development of astronomy by working as laboratory assistants, or as they were referred to, not pejoratively, but as a compliment, computers. They were doing the computation that was necessary for these classification tasks. The original Harvard spectral classification ordered spectra by the depth of the hydrogen absorption lines. Chemists recognized the wavelengths associated with hydrogen gas from laboratory experiments, and astronomers quickly realized that hydrogen was often a very characteristic absorption line that they could readily identify in the spectra of stars. What Pickering and his principal assistant, Williamina Fleming, did was to start by assigning stars which had the deepest, strongest hydrogen absorption lines to spectral type A. They then proceeded to go through the alphabet, B, C, D, all the way up through N, classifying stars by having progressively weaker hydrogen absorption lines. So you would look at a star, you would find the hydrogen absorption lines at the characteristic wavelengths, and you would judge the depth of those hydrogen lines. You judge this by eye, by looking at the darkness of the line on photographic plates, something that a person can be readily trained for and in a few weeks can become quite expert at. And indeed, Williamina Fleming became extremely expert at this and noticing these various patterns. The problem of this classification sequence, however, was that there were many other lines that appeared in the spectrum. For example, the lines of helium, the lines of iron, magnesium, and sodium, and so forth. But while you could simply assign A, B, C, D up through N class to the strength of the hydrogen absorption lines, it was quickly noticed by Fleming and others that the other absorption lines didn't seem to show any particular patterns to them. And this caught the attention of one of the computers who worked for Pickering, Annie Jump Cannon. In 1901, Annie Jump Cannon, who originally began work as one of Pickering's core of computers, noticed that the spectral patterns that she was seeing were related to the color of the star, and of course color is related to temperature. So Cannon undertook a reorganization of the Harvard classification system. She took the ABCD classification that was developed originally by Pickering and Fleming and reordered the stars by the appearance of their color, which was really by the appearance of their temperature. She found that many of the various classes were actually redundant. They weren't necessary, and she greatly simplified by removing these redundant classes and boiling the system down to 7 fundamental spectral types. Now ordered instead of in order of hydrogen line strength, A, B, C, D, were ordered in order of temperature from hottest to coolest as O, B, A, F, G, K, and M. Only these 3-letter classes were retained of the original ABC through N classification developed by Pickering and Fleming. Cool, very faint stars, which were discovered during the late 20th century, were found to not fit within this classification system. They were cooler than M-type stars and were assigned to a new spectral type, L. In recent years, proposed classes T and Y have been applied not to stars, but to objects called brown dwarfs, failed stars, or perhaps even giant gas planets around other stars. But for our discussion, we're going to leave out the T and Y classes. This is the spectral sequence developed by Annie Jump Cannon. They're arranged in order from O, B, A, F, G, K, and M in the original Harvard classification. A subsequent analysis of the classification added a number to the classification, 0 through 9, recognizing that there were subtle differences between different types of stars that were classified as A, F, G, and so forth. This allowed a finer gradation of the series so that between O to M there are approximately 70 individual types of stars, and indeed, as you can see from this photograph, 6.5 is used by some astronomers. You can see in the color representation here, the stars go from O, which predominantly have blue light fading out to faint in red, all the way up to M, which have very strong red light but are very, very faint in the blue. And you can see the diagonal band of color running from blue, indigo, green, yellow, orange, and red is showing a sequence of decreasing temperature from hot blue stars at O to the coolest red stars at M. You can also see what Cannon saw. She noticed that in addition to the hydrogen lines, like the hydrogen line here, this is the red hydrogen line, she noticed that indeed the spectral sequence A through G was stronger, but these other lines form patterns where lines may start out weak, get strong, and then grow weaker again in sequence, whereas other lines may be practically absent, but start growing stronger and stronger still, or stronger and weaker and reappearing through the sequence. It was recognizing these patterns in the spectral lines that was Cannon's deep insight. This patterning of lines is no accident. It turns out to be related to the temperature of the atmospheres of these stars, because what atoms are present in what atomic states is determined by the temperature and pressure inside the atmosphere of the star. While Cannon was working in an age before we had quantum mechanics and an understanding of the workings of atoms and molecules, she nonetheless gained a key insight into the nature of atomic physics, an insight that was to prove invaluable in the 1920s and 30s in the rise of quantum mechanics. But that's a different story for a different day. Today we want to set just to this idea of spectral classification. The fundamental idea is that the spectral classification sequence is a temperature sequence. The classification O, B, A, F, G, K, M, and L are stars that are running from the hottest stars, around 50 to 60,000 degrees Kelvin for the hottest O stars, down to about 1,300 to 1,000 degrees Kelvin for the coolest L and M stars. They're also ranging as a scale of spectral color, so that the bluest stars are the hottest stars and the reddest stars are the coolest stars. So O stars are blue, M and L stars are red, and the other classifications, B, A, F, G, K, M, lie in between in individual colors. Before the development of accurate photometric methods to measure colors, the use of photographic spectra to classify different stars into types O, B, A, F, G, K, M, and L, and thereby sort them in order from increasing to decreasing temperature, was the only way we had to estimate stellar temperatures. In the modern age, quantitative photometric methods, especially those using electronic detectors, have largely replaced stellar spectra as the primary way of assigning types and temperatures. Although, in reality, even spectral color, measured photometrically, is not the most accurate way to measure temperatures. It actually requires the detailed analysis of spectral absorption lines, which species are present in what strengths, that can give us the most accurate measurements of temperatures.